Welcome to class time.
I am Karima Mundell Thomas.
And I am Latoya Shiraya. The secret of getting ahead is getting started. So let's start.
Let's start indeed.
All right, so as you said, Karima, we'll be looking at calculating the volume of solids, in particular, right pyramids, cones, and spheres.
Yes.
But
we want to talk a little bit about volume and capacity.
Yeah.
I think we mentioned it in a previous lesson, but just to ensure that our students are on point with what we're going to be looking at. All right, so listen carefully. Now, the volume is the amount of space, right, that's taken up by a substance, whether it's solid or otherwise. All right, so a solid substance. It can be. Now, we talk about capacity as well, being the measure of an object's ability, Latoya, to hold a substance like solid, liquid, or gas. So basically, when we talk about capacity, we're thinking of something like a container. It has a cavity that can hold something. And there is a point when the volume and the capacity are actually equivalent, because if I should fill a container to the brim, as we would say in Jamaica, you know, it would have been filled to capacity. All right?
So what I'm hearing you saying, Karima, is the capacity in Jamaican language is how much it can hold. All right. And then the volume is how much in the air.
All right. We can work with that.
All right.
And we're saying it can be equal if it full to the brim.
Not a
Both
problem.
can be equal.
All right.
So let's recap. Because though we're going to be looking at pyramids and spheres and cones,
right,
it's important that we do a recap about volume of prisms.
Which we would have done already.
Yes. So let's just do a quick recap. So the volume of a prism, it's found by the area of its cross-section being multiplied by its perpendicular height or length. So here we have a rectangular prism, and I'm sure we can see the cross-section highlighted in yellow. Yes. So the area of that cross-section would be length multiplied by width. And of course, we know now to find the volume, we must multiply by the perpendicular height. Now, we also have a triangular prism. Also, the cross-section is a triangle now in this case, and it's also in yellow. I think we love yellow today. But to find the volume, again, we need to find the area of the cross-section. So here, the cross-section is simply a triangle. So it's half the base multiplied by the perpendicular height. And I want to point,
triangle.
You just took it from me. I wanted to point out that this perpendicular height is the perpendicular height of the triangle.
Right.
Once we have done that, we multiply by the perpendicular height of the prism. There you go. All right, so just a quick recap. Now, we also looked previously at the cylinder, how to find the volume of a cylinder. And though we said the cylinder wasn't a prism, or it was, as you would put it, prism cousin, right? We looked at it and we saw that it operated on the same premise. And so here we're seeing the cross-section to be a circle or circular. Yes, so it has a circular cross-section. And so we can find its volume using pi multiplied by r squared, which will give us the area of the circular portion, multiplied by the perpendicular height. And again, it's the height of the cylinder in this case.
All right. So we're moving on to finding the volume of pyramids. So we know how to find the volume of prisms. Now we're moving on to pyramids. But what are pyramids? So
I'm thinking back, and as I see the word pyramid, I think of Egypt.
I think of the mummy.
Immediately. But fun and joke aside, when I think about the pyramid, I think of a particular solid. So I know there's a base, and I'm thinking that, you know, there usually are triangular faces that actually meet at a point right up the top there. I think it's called an apex, but I could be wrong. So you tell me, because that was a long time ago.
A pyramid is a polyhedron that has a base and 3 or more triangular faces that meet at a point above the base, as you said, called an apex. So here we have an image, and this is a representation of a square base or rectangular based pyramid. And right at the little top at the peak there, that is our apex.
I want to point out though, Latoya, before you move to the next point, when we looked at Prism, we saw where the Prism had a uniformed cross section.
Right.
Yes, so as we go to the cube that we have on set, we would have seen that it has a uniformed cross section. So if I'm using here, we're seeing the same shape, same size, same everything right throughout the Prism. However, when I look at the diagram that you have on the screen, and also when I take up my pyramid that I have here, I'm seeing that, so in this case, the base is a square.
Right.
Yes? But I'm seeing that I'm not getting the same size square right throughout because it's coming up to a point, these squares, the square shape there, it's getting smaller and smaller and smaller until it gets to the top.
Right.
So that's a very important distinction between the prism and the pyramid.
Pyramids. Okay.
And it's in the picture. Sorry to cut you. It's actually the picture with the several colors actually showing us what's happening.
Right. The shape of the base gives the pyramid its name. And in this case, as you also use the manipulative there, this is a square-based pyramid.
Yes.
Right? As you can see. Here are some other examples of pyramids. We have the rectangular-based pyramid, the triangular-based pyramid, or a tetrahedron. This is a special one, so it has its own name.
Yes.
Tetrahedron. And then
hexagonal.
Hexagonal-based pyramid. Okay, so as you are seeing that there is a different shape at the base, and then we have the triangles going up, or triangular faces going up to meet at the apex.
There you go. Perfect.
All right. I have a scenario for you, Karima.
All right. I love scenarios.
So, two vendors, Miss Patsy and Miss Joan, are selling French fries at a school gate. And we students, you know the shapes, right?
Yes.
Both vendors use the same size scoop to serve a measure of French fries.
All right.
Miss Patsy twists her paper to make a cone for her chips. Nice and fancy. But Miss Joan twists her paper to make a cylinder for her chips, or a cylindrical shape for her chips. Why do customers think that Miss Patsy is more generous? I mean...
Well, immediately as you're talking about Miss Patsy and Miss Joan, I started to think about when I used to purchase ice cream. And I usually think, boy, I prefer buy the ice cream on the cone, you know, I'm not lie. Because when it buy in the cup, it always look less.
Just drop down in the cup, so.
Yes. So I'm thinking that this might be something similar to what Miss
Patsy or Miss Joan?
Yes, Miss Patsy, no, the cone. Miss Patsy probably used something like this for her chips.
Yes.
So, me think the chips them not really drop down in the bottom too.
That's why it looks like enough up on the top, because the space is smaller.
Down here, so.
Okay.
That is my opinion now, you know, but I could be wrong.
All right, so when I think about cylinders and cone, I'm wondering if they have a relationship.
Never thought of that before, you know, but there may actually be a relationship.
The capacity of a cylinder, given that it is the same,
the cross section is the same as the base of the cone.
And the heights are the same.
And the perpendicular heights are the same.
Then the capacity of 3 cones will be the same capacity as 1 cylinder.
Good, but those conditions must be met. So let us just emphasize those conditions a little bit more.
So when the perpendicular height of the cylinder and the cone are the same.
Right, condition 1.
As well as the area of the cross-section of the cylinder and the area of the base of the cone are the same measures.
Then
the capacity of the cylinder is 3 times the capacity of the cone.
Exactly. So of a single cone, there you go. The capacity of the cylinder is 3 times. There you go. So what I want to know, because the focus of today's lesson is really not on the cylinder.
Right.
So how do I use this information to actually figure out how I can find the capacity or the volume, let's say it full,
right,
to capacity? How do I calculate, how do I figure out what is the volume or capacity of a cone?
All right, let's start with what we know.
All right.
So we know that we can multiply pi multiplied by r squared.
And r here is the radius.
Yes, multiplied by the perpendicular height, we can find the volume of a cylinder. So then if 3 cones of the same perpendicular height and base will get 1 cylinder, then I'm thinking that we can use 1/3 of the volume of the cylinder to determine the volume of the cone.
True, come to think of it, remember that 1/3 really means that we're dividing this thing in 3 equal parts.
Right.
So really one of those thirds would actually be equivalent to what she poured from 1 cone.
Right.
Makes sense.
So if we were to share the water that was in the cylinder in 3 equal parts, then that would be the volume for 1 cone, the volume of water for 1 cone.
One of those parts would be the volume of. Yeah, makes sense. So let's continue. I'm loving this exploration. Let's proceed a little bit further.
So now that when I think about the cone and the cylinder, and I'm seeing the relationship there, I'm thinking about a rectangular based pyramid and a cuboid.
You think there's a relationship?
I don't know. Let's watch this video and find out.
I want to find out. I'm like so curious right now. So in this video, Latoya, we're seeing a rectangular based pyramid. It could be a square, but we're not so sure. So let's stick to rectangular based pyramid. And we're seeing a cuboid. Again, it could be a cube, but we're not sure. So let's stick to cuboid. Now, again, the area of the base and the area of the cross section are equivalent, and the perpendicular heights were also equivalent. So we're seeing the pyramids being filled with some liquid. So he has poured in 1 pyramid in, 2 pyramids in, 3 full, sealed to the brim pyramids in, and it's full. The prism is full. Now we're seeing a triangular prism and a triangular based pyramid. The base and the cross section are the same, and the perpendicular height is the same as well. And you notice he's checking all of that before he pours water into the pyramid. So it's full to the brim, and he has now poured that into the triangular prism. He has filled a second pyramid, and he has poured that too in the triangular prism, and it's not full yet, Latoya. It's not yet full. This is the 3rd pyramid he has filled, and he has poured it in. I want to see if it's full. Oh yeah, there it is. It's full, Latoya, to the brim.
Interesting.
Interesting indeed.
Interesting.
That kind of sound, it looks similar to what we just saw, doesn't it?
It did.
Yeah, but let's talk a little bit more about it.
So based on the video, we saw that the capacity of water that was in the rectangular based prism,
or the cuboid,
yes, the cuboid, that was filled by filling 3 rectangular based pyramids of the same perpendicular height, and the area of the base of the pyramid and the area of the cross-section of the cuboid were the same.
Yes, similar to what we saw before.
Right, so basically when the perpendicular height of the cuboid and the rectangular base pyramid are the same, as well as the area of the cross-section of the cuboid and the area of the base of the rectangular base pyramid are the same measures.
Yes, then something magical happens.
The capacity of the cuboid is 3 times the capacity of the rectangular based pyramid.
Ah.
Wow.
That's interesting.
Yes.
But you know where I'm going to go, right?
No, where are you going?
I already know how to find the volume of a cuboid.
Okay.
My purpose here today is for you to tell me how to find the volume of a pyramid.
Well, we saw it just now.
Yeah, but all I know is that it took 3 pyramids full of water to full a cuboid.
So if it took 3 to fill the cuboid,
dimensions.
How would I find 1? We know how to find the volume of a cuboid.
Right. Right. I need to, you know, find 1/3.
Shear it up into 3 parts.
Yes. Makes sense. I should know this, you know, because
so
it's
we
like
can
so
find
similar.
the volume of a rectangular based pyramid by finding 1/3 of the volume of a similar cuboid by multiplying the length by the width and multiply that by the perpendicular height. So area of the cross section multiplied by the perpendicular height.
Yeah, and then we just find 1/3 of that.
Find 1/3 of it.
Makes sense. So you see, I don't think we had actually talked back about Miss Patsy, you know. We didn't actually conclude why the students felt that way, but I think we can mention it now that when Miss Patsy, I hope it's the Miss Patsy, but you know, the one that did the cylindrical container, when she put her fries in there, it only went to 1/3 the height of the cylinder.
That is why.
And then the other one who used the cone, fair one look
1/3 of the capacity.
Yes, the capacity. Thank you.
Yes, that is why.
Yeah, we definitely had to go back to that.
But it's the same scoop.
There you go, same scoop.
All right.
But the children don't know that, you know. So.
All right. We also saw in the video where the relationship between the triangular-based pyramid and the triangular prism were
the relationship was explored.
Yes, we did see a relationship. And just like the cylinder and the cube and the cuboid,
the cylinder and the cone,
and the cuboid and the rectangular-based pyramid, the relationship is the same with the triangular-based pyramid and the triangular prism. But we have to remember these very important conditions.
Definitely.
So, when the perpendicular height of the triangular prism and the triangular-based pyramid are the same, that's one condition. Condition 2, the area of the cross-section of the triangular prism and the area of the base of the triangular-based pyramid are the same measures, then the capacity of the triangular prism is 3 times the capacity of the triangular-based pyramid. And we can use that information to help us determine the volume or the capacity of a triangular-based pyramid. So we know how to find the volume of a triangular prism, and since the volume of a triangular-based pyramid with those conditions applied, then we would find 1/3 of an assumed similar triangular prism of the volume of that triangular prism, as you can see on screen.
And I want to point out again that I don't want students to be confused when they're seeing perpendicular height being written twice. It's not referring to the same dimension. Remember the section that's in brackets. So as we look back on the screen, remember when we're talking about the triangle would have had a height in and of itself, a perpendicular height. And so we want to ensure that our students are not confused when they're looking at what we have on screen. So half the base multiplied by the perpendicular height, we're referring to the base of the triangle.
Right.
And we're referring to the perpendicular height of the triangle. And that would now give us
the pyramid
area. No, I'm talking about what's inside the bracket now.
Okay.
So we're talking about half base multiplied by perpendicular height.
Okay.
That deals only with the triangle, the shape, the triangular portion.
Area of the cross section.
The cross section. Beautiful.
Great.
And notice that when we have on the outside now of that bracket, we have another perpendicular height to consider. And we have put it in red for a reason. Because this perpendicular height is referring to the height of the prism. Or when we're looking at the triangular-based pyramid, it would be referring to the height of the pyramid. And we're talking perpendicular height. So I want to just go back to what we have on our table, just to review, because I think when we come back from the break, we're going to be looking at some questions. And I would want us to just summarize what it is that we have looked at so far. So we have found some interesting relationships. So far, unfortunately, we don't have a triangular prism or a triangular-based pyramid. But we found out something today, students. We found out something today. we found out that if we wanted to find the capacity of this square-based pyramid, yes, and we compared, as a matter of fact, the capacity of this square-based pyramid to this cube, in this case. And we found that once the base of the pyramid is the same as the cross-section of the prism,
yes,
and also if we were to put them, let me ensure the camera is picking up, if we were to put them beside each other, these might not be exact at the moment, but it's man-made, but we're getting the idea. If we were to put them beside each other and actually check the perpendicular heights, if we find that they are equal,
yes,
then the capacity of the cone, not the cone, the square-based pyramid,
yes,
is actually 1/3 the capacity of the cube.
Yes.
Am I correct? Did I say that
Very
correctly?
correct.
Beautiful.
So you know what I love about this, Karima? We don't need to try and remember all these different formulas. If we can remember the relationship, we don't need to study the formulas.
Yes, and I'm not one for swatting,
yes,
you know.
Yes.
I really can't do it.
Yes.
So we also found a similar relationship between the cone and the cylinder when
yes,
we're talking about the volume or the capacity. And we saw that once the cross-section and the base of this are the same and their perpendicular heights were also the same, we noticed that the volume of the cone
is
actually 1/3 the volume of the cylinder.
So we're going to be using that information now to see if we can answer some questions. The paper cups used at a water cooler is in the shape of a cone of radius 3 centimeters and height 10 centimeters. Calculate the volume of water in the cup when it is full, and we're taking pi as 3.14 or 3 14/10ths.
What do you know? I actually have one of those cups right here.
Okay.
Yes. Yeah. So, we've been given the radius, correct?
Yes, we were.
3 centimeters.
Yes.
And the height of 10 centimeters.
Yes.
All right, let's see what we have here.
So we need to determine the volume of the water cup. So the cup is in the shape of a
cone.
A cone. And we know that we can find the volume of a cone by multiplying 1/3 multiplied by pi multiplied by radius squared multiplied by its
perpendicular height.
Yes, ma'am.
All right.
All right.
So from here, it's pretty much substituting because we know we're given what to use for pi, 3.14 or 1400, as you pointed out. We have the radius of 3 centimeters, and we know the perpendicular height is 10 centimeters. And remember, it's radius squared. The radius is squared.
Yes.
Make sure, students, that you pay attention to that. All right. So once we calculate 94 and 2/10 or 0.2 cubic centimeters.
And I just want to point out as well that all we did was to assume that the cone had a similar relationship with a cylinder.
Well, we're not assuming. We're saying if we had a cylinder that had the same circular portion in terms of the area and the perpendicular height were the same, then we're sure that this relationship exists.
1/3 of the volume of that cylinder.
There you go.
Would be the volume of this water cup here.
All right. So we can basically proceed with another question.
Okay. So a cereal company is changing the package of their mini cereal package. You know, the little small
the one you can just drop in a lunch bag. Yes.
Yes, man. They are trying to decide which of two packages will hold more cereal. Determine which of the two packages will hold more. So we have a square-based pyramid for package A, look. And then we have a triangular-based pyramid for package B, look. And we need to determine which will hold more. Okay, let's do a bit. Which one you think going hold more?
You want me choose first? You sure?
Okay, I choose the square. I think the square base pyramid going hold more.
I know you were going to choose that, you know, that's why I make sure to ask you. So since you've chosen package A, I'll choose package B. Don't worry, no sweat.
So we will look at the capacity of each package and then we will see. So here we have a square base pyramid and we need to find the capacity.
All right, and since we're assuming that the cereal that's going to be in there will be full to capacity.
Yes, yes.
We have actually used the word volume here.
Yes.
All right, so the volume of the square-based pyramid is going to be 1/3, whatever the area of the base is, multiplied by its perpendicular height.
All right.
All right, so it's a square-based pyramid, and so we know that the base is a square, so obviously both length and width are equivalent or equal. So we have substituted our 5 centimeters there, and also our 8 centimeters for the perpendicular height.
Yes. And then it's simplification.
All right, so 66 7/10 cubic centimeters.
Yes, ma'am. Okay, so you say you're...
You try and memorize that number.
All right,
okay?
no problem.
Okay.
So I'm 66 7/10.
All right.
Okay?
Let's
cubic
see.
centimeters.
Let's talk about my package. Package B, the triangular-based pyramid. So I'm looking at the triangular-based pyramid, the diagram there, and I'm noticing that on the triangle we have a base of 5 centimeters and a perpendicular height on the triangle, that is, remember, of 8 centimeters. And I'm also seeing a perpendicular height of 10 centimeters as it relates to the pyramid itself.
Yes.
All right? So the volume of the triangular-based pyramid, again, 1/3 the area of its base multiplied by its perpendicular height. And again, we can substitute. So notice we have kept a portion in bracket. We're just following through from the relationship that we discovered. All right? So it's not that you have to multiply in that particular order, but based on what we've been discussing, we have chosen to do it this way. So it's half multiplied by 5 centimeters, multiplied by 8 centimeters, multiplied by 10 centimeters, and then we're finding 1/3 of that result. So 1/3 of 200 cubic centimeters. This is very funny because that looks like what you had for your package.
Really? And I thought I was going to win. All right, so basically then, both packages will hold the same amount, even though they are two different solids.
Yeah, but you see, that's the beautiful thing about measurement, because we notice now that when we looked at the square-based pyramid, the dimensions weren't, let me not even say necessarily, they weren't the same as the dimensions that we have on this triangular-based pyramid.
Right.
But when we actually completed the calculations, we noticed that both packages will actually hold the same amount of cereal. This is interesting.
This is math. It's beautiful.
Yeah, and I don't have to part with anything because you didn't win the bet. So let us continue with our lesson, because when we looked at the objectives, Latoya, we said we were going to be looking at the volume of pyramids, cones, and spheres.
We did pyramids.
Yeah, did cone.
Now we're on to
the sphere. Okay.
And I'm thinking, since that we started on a trajectory of finding relationships, I'm now looking at the sphere on the table, and I'm trying to figure out which other solid could I find a relationship with.
Well, guess what? How we sectionalized the solids on the table has something to do with which ones are related. So let me remove my paper one that I just used. How those are on the table, they're actually sorted, so to speak.
All right, so from that clue, I'm going to choose the cone and the sphere.
So you think this cone is related to the sphere in some way?
I think so.
All right, as usual.
But then if the cone is related to the sphere, that means that the sphere is related to the cylinder because the cone is related to the cylinder.
But hold on. One step at a time, darling. Let us figure out, first of all, if there is a relationship between the cone and the sphere.
So what I saw you did earlier in finding relationships, I saw you line them up.
All right.
Like so. Okay. The sphere not going to stay because it's spherical, round. Okay, so it kind of seems like the heights are the same. All right. Seem as if the area of this half circle and the
so they're basically looking like they have the same radius.
Yeah. Yeah.
You know what? Latoya, I think we need to watch a video, as we've been doing.
That is true. I'm not going to rely on my own knowledge.
Oh, yes, and we don't have anything to measure really right here. And, you know, it would be good to have some liquid to see what's happening.
So we're going to watch a video together and then.
So we're seeing in this video, Latoya, notice your sphere couldn't stand on its own, you remember?
Right.
So he has actually propped it up on a prism. No need to pay attention to that. And he would have done the same checks that you did. So the height of the cone here is equivalent to the diameter of the sphere, and the radius of the base of the cone is equivalent to the radius of the sphere. Now he has filled the cone. Now, but the cone, being its circular nature, it's hard to pour from, not true?
Yes.
So he has basically just transferred the water into a pyramid just to make it easy to throw it out, you know, the little corner part, you know. So he's now filling a second cone.
So one full cone was already thrown in.
Yes.
And now a second cone is being thrown in. Cone of water, right? Water. Karima, it full.
It full. Oh my God.
It is filled to the brim.
Yep,
Wow.
it is. You know, every time I see these things, my love for math just, you know, it skyrockets, you know. But let's talk about what we saw in the video, though. What kind of relationship did we see coming out?
So the height of the cone and the height, or we can say the diameter of the sphere were the same.
Yes. And the radius of the
by
base
nature
of the cone,
of the fact that the diameter are the same, then the radius will also be the same.
All right, so the radius of the base of the cone, right, is equivalent to the radius of the sphere.
And then the volume of water from two cones.
Full to the brim.
Full to the brim.
Full up the sphere.
Full up the sphere.
You know what? We've prepared something just to explain how we need to now derive how we form, what formula can we use. We have to derive from what we saw.
Okay.
So let's go back to the screen and see if we can watch carefully what's happening on this slide. So we're summarizing.
Okay.
So walk us through, just click quickly, and let's see what's happening here.
So first we have two cones and we have a sphere, representation of a sphere.
All right, so we're going to do some checks now because remember we saw some conditions coming out in the video.
All
so let's do our first check. So we have the radius of the base of the cone and they're both the same. And it's matching with the radius of the sphere.
Check.
Check. All right.
All right. And we also know that to find the volume of one cone,
yes,
that would be 1/3, taking the area of its base multiplied by its perpendicular height, represented by pi multiplied by r squared multiplied by its perpendicular height there. So we are now representing the base of the two cones.
The volume of the two cones.
The volume of the two cones. Thank you very much.
Yes.
The volume of the two cones.
And we saw that when those were put together, as we saw in the video, he poured from two cones into the sphere.
Yes.
So we can say then that the volume of these two cones was actually equivalent to the sphere.
All right.
And we checked the radius a while ago.
Okay.
So let's check a few other things. So let's check the height of the cone.
Same as cone number 2.
Yes.
Also the same
as the diameter. of the sphere.
Hey.
Yes.
Okay.
So then, what do we know about diameter?
That's 2 radii.
Ah, watch this. Just look, girl. I mean, this is so exciting.
Okay.
So we say, yes, radius number 1, radius number 2. So we have 2 radii. So Latoya, look back at what you have below each of those cones, right? And tell me if you think I could swap out. I don't know if that's the right word, but we're Jamaican. We understand. Replace.
Substitute.
Thank you. The height that we have here, I replace it with 2 radii.
Because this now means that the height of the cone is equivalent
to 2 times or 2 of the length of the radius.
That is true. So we are replacing in our formula for the volume of a cone, we're replacing the perpendicular height with 2r.
2r.
So we are now representing h as 2r.
So we can simplify what's happening up there because we had r square initially and now we have 2r there. So we can put it together nicely now.
Right,
because
we're multiplying.
We're multiplying.
Yes.
Beautiful. So we have 2 multiplied by pi. Oopsie, it's gone, right?
No, so it's right.
Oh, you're going through again.
Going back, right. So just want to show, just in case you missed it, that we realize that there is a relationship between the height of the cone and the height
and the diameter of the sphere.
Of the sphere, which is now 2 radii.
Right.
So we're replacing that perpendicular height with 2r representing the 2 radii. And now we're going
multiply and simplify what's in our numerator.
So we don't have to have all this confusion. We have r's, so we can group the like terms.
So we're multiplying throughout, right?
Yes.
And so we have a simplified numerator here, Latoya.
Yes.
2 pi multiplied by r cube. And it's 1/3 of that.
Okay.
And we remember that it took 2 full cones to fill up the sphere. So we need to put that together. And one of the beautiful things, it looks fractiony, not true?
Yeah, man.
So we have numerator, we have denominator.
Yes.
And we're noticing our denominators are the same. Beautiful thing about fractions now, we can just add our numerators. So let's add. I tell you, this is so exciting. So basically, Latoya, what we've just discovered is that to find the volume of a sphere, it is really 4/3 pi r cube. Interesting.
Interesting indeed.
You know, I can't wait to use up this information. So guess what? Let's put a question up on the screen. Let's read it. And we're asking our students to do this one.
And if you get it correct, pat yourself on the shoulder.
That's right.
All right. So it said a pastry company makes spherical chocolate balls. The diameter of each ball is 3 centimeters. How many chocolate balls can be made from 710 cubic centimeters of melted chocolate?
And we're told to take pi as 3.14.
Yes.
Now, before the break, Latoya, we found out a quick way. We discovered, how to find the volume of a sphere.
Right.
And we're talking about spherical chocolate balls.
Yes.
All right, so I think we need to,
and round.
Yeah, we need to use up that formula that we just derived to assist us here with this question. So,
but what's the first thing we need to do though? Because they're asking us how many chocolate balls can they make from 710 cubic centimeters of melted chocolate, but we don't know.
So we need to first find how much melted chocolate they need for one ball.
Okay.
Yeah, we need to do that. And I'm noticing something else, lots, because it says diameter of each ball is 3 centimeters. And bring up what we just discovered, please. Volume of a sphere is equivalent to 4/3 pi r cube. Don't see any D in there, don't see any diameter. So we need the radius, girl.
Yes, but that's easy, man.
Yeah, I was about to say that. Half of the diameter, half the length of the diameter.
But that's a very good observation because that is one of the errors, very common errors that our students make, where they just take the values from the question, insert them into the formula without operating on them. Sometimes you have to do a little small procedure.
Yes.
Yes, to get to your correct
So our
answer.
radius is 1.5 or 1.5.
Yes.
All right.
And we're just substituting our values. They already told us what to use for pi, which is
Right.
3.14. And we're multiplying that by r cubed, and or r is half of the diameter as told, which is 1.5. Simplifying, so we're now multiplying 4/3 by 10.6. And so the volume of chocolate that is needed to make one chocolate ball would be 14 1300ths or 14.13 cubic centimeters of chocolate ball. That's not so enough.
We need to figure out when we're finished. We need to figure out how many of these chocolate balls can be made from 710 cubic centimeters. So let's see if we can get there quickly.
All right. So we know that it takes 14.13 cubic centimeters to make one chocolate ball.
Yes.
So if I have 710 cubic centimeters of melted chocolate, and I want to know how many chocolate balls can I get out of that?
I need to see how many 14.13 I can get out of 710.
Simple thing, man.
Yeah, I need to divide.
Yeah.
Beautiful. So how many chocolates?
So when we divide 710 by 14.13, we're getting a value of 50.25.
But they asked us how many chocolate balls. I don't think they're going to sell quarter chocolate balls.
Who is going to buy that?
so let's just give this approximation. So pretty much 710 cubic centimeters of melted chocolate will actually or can actually make 50 chocolate balls.
All right.
I think we're ready to summarize. We've done a lot today.
A lot. Yes. But I love the exploration. It was fun.
Me too. Yeah. Me too.
So, okay, so based on all that we would have explored,
yes,
what can we deduce, summarize, generalize?
The thing that we want our students to remember after today. Now, the volume of a cone is equal to 1/3 the volume of the cylinder with the same perpendicular height and the same radius. So we remember those conditions.
I have to.
So the perpendicular heights must be equal. And we mentioned the radius of the cylinder and the radius of the base of the cone must be equal as well.
All right.
All right. We would have discovered before volume of a cylinder is pi r, is found using the formula pi multiplied by r square multiplied by perpendicular height.
Or multiplying the area of its cross-section by its perpendicular height.
So therefore, for the cone, if we're saying it's 1/3, then it's pretty much 1/3 multiplied by pi multiplied by r squared multiplied by perpendicular height. In other words,
Singstress.
1/3 the area of the base multiplied by its perpendicular height.
Yes.
All right, so let's see what else we discovered quickly.
All right.
Now, we also discovered, Latoya, that the volume of a pyramid is equal to 1/3 the volume of the prism with the same perpendicular height and the same cross-section or base. So we know cross-section, we're talking about the prism.
Yes.
Base, we're talking about the pyramid.
Yes.
And I think that picture says a lot, right? So it's a similar relationship that we found earlier. So the volume of a pyramid is equal to 1/3 the area of its base multiplied by its perpendicular height. And we made one last discovery. You want to say something before?
Yes. Remember when we're looking at the triangular pyramid and the triangular prisms, we have two perpendicular heights to take into consideration.
Right.
And we have to distinguish the perpendicular height of the
triangle,
the cross-section and the base, separate from the perpendicular height of the solid itself.
Beautiful.
Right.
And lastly,
yes,
the volume of a sphere is equal to the volume of two cones whose diameter and perpendicular height are equal to the diameter of the sphere.
Yes.
All right, and we would have explored that
earlier.
We did. So the volume of the sphere is 4/3 pi r cube.
Whoosh.